The hash table is a fundamental data structure in computer science. If you've ever wondered how search engines can find results so quickly, it is all thanks to the hash table data structure. First, we will discuss the history behind hash tables, and then we will explore the internal workings of a hash table in terms of how they store data, as well as how they retrieve it. And once you learn the fundamentals, I will provide you with a workbook where you can practice coding your own hash table. We will begin with some historical background because we cannot discuss hash tables without traveling back to the 1950s and introducing Hans Peter Lund. Hans was a mathematician and an inventor at IBM. As an inventor, he had the freedom to tackle any problem that he liked. But his contributions in accelerating the search for data were nothing short of revolutionary. In 1953, he proposed the model for storing information inside buckets, which is considered a precursor to the hash tables that we widely use today. I think we should take a closer look at Hans's ingenious idea. Imagine you're building a program to search a database of phone numbers. The straightforward approach would be to store the phone numbers in a list and then compare each element against a target value one by one until you find your match. This technique is called linear search, and it works well for small datasets, but with a large database like 1 million records, searching through it one by one would be very slow and very inefficient. So Hans suggested a more efficient approach. Instead of storing phone numbers in a plain old list, he proposed dividing them into buckets. And to determine the bucket that a phone number would belong to, Hans would apply a mathematical operation. This operation groups the digits into pairs, adds them up, and keeps only the last digit if a number has more than 1. The original phone number is then placed into a bucket that matches the final result. Although this phone number is different, applying Hans's operation of pairing the digits, taking the sum, and keeping only the last digit if there happens to be more than 1 will still place it inside the same bucket. I will apply this process to 15 phone numbers, resulting in a total of 5 buckets for all 15 numbers, and I hope you can see how dividing the database into these buckets significantly reduces the searching space. Because if there is a target phone number to find, then I can apply the same mathematical operation to determine the bucket that contains it. And now, instead of looking through 15 phone numbers, I only have 5 buckets to look through. Once I find the bucket that the phone number is in, I only have to compare the phone numbers within the bucket to my target value and return the phone number that matches it. This method of storing data in a table of buckets is a precursor to the hash tables that we commonly use today. So as we look at the inner workings of a modern-day hash table, you're going to notice many similarities to Hans's model. First, we're going to go through the process of storing data in a hash table. You can store entries in a hash table. An entry is a key-value pair. The key is used to locate a specific piece of data, while the value represents the actual data of interest. Internally, the hash table is supported by an array of buckets. At first, the array doesn't have the capacity to store anything. However, as we insert the first entry into the hash table, the array must be resized to accommodate the new data. For this particular hash table, an initial capacity of 16 has been assigned, where the capacity represents the number of available buckets. Step 2 is to produce a hash from your key. A hash function is a mathematical operation that takes a key as input and generates a unique value known as a hash. the hash value will be unique for different inputs. We insert our first entry, a banana, for $2.99. Because this is the very first entry, the hash table is going to start by resizing to 16 buckets. We can confirm that. Then the hash function is going to process the key and produce a unique hash. We can repeat this process for 2 more entries. And you'll notice that the hash value is going to be unique for different inputs. And here we've got the hash value for lime. The hash of a key determines where the entry will be stored. The hash value that corresponds to the key lime is, in this case, 2 quintillion, and somehow from this hash value, from this astronomical number, we need to extract an index that ranges from 0 to 15. This can be achieved by performing a bitwise AND operation between the length of the array and the hash value itself. Performing a bitwise AND operation involves representing both numbers in binary form, zeros and ones. 15 in binary is 4 ones. The hash value, 2 quintillion in this case, in binary is this monstrosity. And since the first binary number only has 4 bits, we can ignore all the bits in the second binary number that come after the first 4. And the way a bitwise AND operation works is that if both numbers are 1, the result will be 1. If either of the numbers is not 1, the resulting value is 0. After you calculate the result, you can convert it to a human-friendly format, and remarkably, the operation produces a valid index. The reason for this is that the bitwise AND of any 2 numbers will always produce a number less than or equal to the smaller 1. Therefore, by performing a bitwise AND operation between the length of the array and the hash, the resulting value will always be less than or equal to the length of the array. This guarantees that the index calculated from the hash will be in a valid range of 0 to 15. We can start by inserting the banana. We will step through the code from before. And here I've got the hash value for banana. If we perform a bitwise AND operation between the length of the array against the really large hash value, that's going to guarantee a valid index inside the bounds of the array. So banana would have been placed inside index number 12 of our buckets array. We can repeat this one more time for lime. Once again, stepping through all the code from before. Here we've got the hash value for lime. Performing a bitwise AND operation between the length of the array against the really large hash value is going to guarantee an index inside the bounds of the buckets array. In this case, the lime entry would have been placed inside of bucket number 10. Step 4 is to insert a node at the index that you calculated. So after determining the appropriate index for the entry, you can store the key value pair in the form of a node. In this case, the hash of the kale key determined that it should be in index 4. And here the hash of the apple key determined that it should go in index 1. The first entry we're going to insert is papaya for $2.99. Skipping through all of these lines. The hash of the papaya key is going to determine that it should be placed inside of bucket number 4. So here, what we do is we store the key value pair in the form of a node, and then insert the node inside of the hash table at the appropriate index. Here we can see papaya for $2.99 is inside of bucket number 4. Beautiful. Let's look at another example. Here we insert lemon for $1.99. Skipping through all of these lines because the hash of the lemon key is going to determine that it should be placed inside of index number 11. So we store the key value pair, lemon for 199 in the form of a node, and then we insert that node inside of our buckets array. And here we can see our entry is inside of bucket number 11. And after executing this line, we can display the inventory inside of our terminal and visualize our buckets. Beautiful. Finally, in the event of a collision, place your node next to the previous one. A collision happens when the hash of a key produces an index that already contains a node. While collisions are infrequent, if one does occur, the solution is to place the new node next to the previous one. In situations where many nodes occupy the same index, what you need to do is traverse the list one by one until you reach a node that does not have a successor. At this point, you can insert the new node. It follows that every element in a hash table points to a list of nodes, also known as a linked list. We can start by inserting the banana entry, skipping once again the lines from before. The hash of the banana key is going to determine that it should be placed inside of index number 8. And what we're going to do is rely on a special method called insertNode to insert our node at the appropriate index inside of our buckets array. Because the bucket at the given index of 8 is empty, it's simply going to place the node at that index. Very simple. Let's fast forward a bit. Now I'm in the process of inserting an entry with a key of lemon and a value of 99 cents. The hash of the key determined that it should be placed inside of bucket number 7, but bucket number 7 already contains a caret node. Because this bucket is not empty, what insert node is going to do is add our new node next to the previous node. So bucket number 7 first contains caret, and next to it we see the lemon node. Step 6 is to resize the array when we exceed a particular threshold. The threshold is equal to a load factor multiplied by the capacity of the array. There are 16 buckets, so the current capacity of the array is 16. With a typical load factor of 0.75, our threshold before the next resize is 12. At this point, I have inserted 11 nodes inside of my buckets array. The size is 11, and so after adding one more node, the size is going to be 12. And now that the size has reached the threshold, we're going to tell our hash table to resize. We can now display our new hash table. And you can see all entries from the previous hash table were reprocessed and re-indexed into the new and much bigger one. Great, we can now proceed with part 3 of our video where we will discuss how to retrieve data from a hash table. In order to retrieve data, you need to know the key that maps to the value that you're interested in. For instance, by passing in the key for yucca, the goal is to retrieve its price value. And you'll remember that the hash of a key determines where the entry is stored. The key gets processed by a hash function to produce a unique value known as a hash. The bitwise AND operation between the hash and the length of the array determine the index where the entry is stored. We found the bucket that yucca is in. The first node inside the index matches the key yucca, so we can return its value. First, we want to get the value that corresponds to the key banana, so we step inside of the method. The key gets processed by a hash function to produce the unique hash that corresponds to banana. The bitwise operation between the hash and the length of the array is going to determine the index where the entry is stored. This tells us that the entry is inside of index number 12. We can check our buckets array, and it is indeed inside of index number 12. We return that node's value, and then we print it. Beautiful. Now looking at another example, if the user wants to know the price of oranges, once again, the key gets processed by the same hash function. The bitwise AND operation between the hash and the length of the array determine the bucket where it's located. And in the event that a bucket has more than one node, we need to scan through each node one at a time until the matching node is located. Once found, the corresponding value can be returned. Now I'd like to retrieve the price of mango. Once again, the key gets processed by a hash function to produce the unique hash that corresponds to mango. The bitwise AND operation between the hash and the length of the array is going to determine the index where the entry is stored. The entry for the key mango is inside of bucket 0, but if we look inside our buckets array, bucket 0 has more than one node. The first node is apple, and the node that is next to it is mango. So what our getter is going to do is traverse through every single node in this linked list of nodes until it retrieves mango and returns it. We can see that in action. The current node is apple. That doesn't match the key that we're interested in, so we skip it. Now the current node is mango. That does match the key that we're interested in, so it's going to return that node's value, $3.99, printing it. And that's pretty much it. You learned how data is stored in a hash table, and then you learned about how data is retrieved from a hash table. I believe you are now ready for the workbook. The workbook will challenge you to code your own hash table using Python. You can access the workbook by clicking the link inside the description. And before I let you go, if you enjoyed this video, please feel free to like and subscribe. As an up-and-coming YouTuber, it would help me a lot.